As in the case for continuous time systems, the frequency response h of omega of discrete time systems can also be approximated by the so-called tanh plot of its transfer function h of z. Let's start with the example transfer function z plus 1 divided by z squared minus z plus a half, which has 1, 0 at z equal to minus 1, and a complex conjugate pole pair z equal to 1 half plus minus j 1 half. In the z domain, this is illustrated by a circle for the 0 at minus 1 and two crosses at the position of the complex conjugate poles. Remember that the frequency response h of omega of the system can be obtained by taking the transfer function h of z of the system and setting z equal to e to the power of j omega. In the z domain, this corresponds to going around the unit circle around the origin in counterclockwise direction. So to approximate the shape of h of omega, remember again that for the poles of the system, h of z is tending to infinity, and for the zeros of the system, h of z is equal to 0. The frequency range between 0 and pi half corresponds to the first quarter of the unit circle. Since here we pass in proximity of a pole for which h of z tends to infinity, the frequency response is drawn upwards, with the peak being exactly in the middle of this frequency range, since the pole has an angle of 45 degrees. The frequency range between pi half and pi corresponds to the part of the unit circle in the second quadrant. Since there is no pole nearby, the frequency response doesn't increase, and for omega equal to pi, the frequency response is equal to 0 due to the 0 at z equal to minus 1. The frequency response for frequencies between pi and 3/2 pi corresponds to the third quarter of the unit circle. Since there is no pole close by, the frequency response only increases slightly. And to approximate the frequency response for frequencies between 3/2 pi and 2 pi, we have to look at the approximation around the unit circle for the fourth quadrant, which contains again a peak since we are passing close by the second pole. Increasing the frequency further above 2 pi means we will continue to go around the unit circle more often, which means that the frequency response will simply repeat, yielding the periodic frequency response of a discrete time signal. Note here that the period in the frequency domain is equal to 2 pi. Hence, the frequency response is given a normalized frequency where the period is always equal to 2 pi. In order to achieve the frequency response in real frequency, where the period in the frequency domain is not equal to 2 pi, but instead omega s, which is equal to 2 pi divided by Ts, the normalized frequency simply has to be divided by Ts, so that we get here pi divided by Ts, which is equal to omega s half. 4 pi divided by Ts equal to 2 omega s. And if you want to receive the frequency response in real frequency directly from the z transform, z has to be substituted with e to the power of j omega Ts, where omega is now the real frequency. Due to this peak, this filter would realize a bandpass filter, which in normalized frequency passes frequency components with frequencies around pi divided by 4. When choosing to implement this DT filter with a sampling frequency of omega s, or a sampling period of capital Ts, this corresponds to having the passband of the filter around the frequency omega s divided by 8.